Hi everyone, my name is Paul and I'm your GTA. So I'm here to demonstrate exactly what's expected of us for Lab 3. So Lab 3 experiment is about understanding the working principles of MSI circuits. So MSI circuits are just a bunch of gates close between 100 and 1,000 gates arrangement to make an integrated chip. So for this particular lab, we need three major components apart from our wires. So we need a 151 circuit, that's an 8-input multiplexer. We need a 3 to 8 decoder, which is a 74138 package. Then we also need a 74161, which is a 4-bit binary counter package as well. So I'll be going straight to demonstrate the required steps for this particular lab. Okay, so one good thing is to understand the orientation of our chips. On the screen, you can see a particular schematic diagram with a single pin label, pin 1, and an arrow pointing to the notch, and a label of the top of the chip. So when you look at your chip from the top, what you're seeing is the notch. And so your pin labeling will start from the left of the chip, which is pin 1, as shown by the arrow pointing to the first pin of your chip. So take note of that. So let's move right into what is expected of us. So for step 1, what we are going to be doing is to verify the correct operation of a 4-bit binary counter. So for this, we will not be using all the output pins of the 4-bit binary counter, but we will be implementing a 3-bit counting sequence. That is, we'll be implementing a count of 0 up to 7 and a roll back to 0, and a sequence count like that. So to make your connection, the manual specifies the connections of each pin to 5 volts and ground respectively, as you can see in table 2. So the pin labels are already there, the pin numbers and the labels. So it's good practice to always connect your VCC and your ground. For your 161, you have your pin 16 as your VCC, which is to the right of your notch. So this is the notch here, as you can see, pointed to by my pen, and my VCC, and then my ground, which is pin 8. So for the wiring convention, I have my grounds as my white wires, and my VCC, which is 5 volts, are connected by my red wires. So yeah, we have a power rail. So your power rail, as indicated by this red line and this blue line, are the 5 volts and the power, the positive end and the negative end. So if you want to connect ground to ground, you can use these power rails to have a common connection, and then you can have the connection to a ground source or a power source for the positive terminal. And that's what we have here. So let's get on to demonstrate the functional operation or the working operation of our 161 counter. So if you do your connection setup well, you should have no problem implementing a normal counter. So for our step 1, I'll be showing us the count sequence on the digital reader, and the clock, which is pin 2 of our 161, is being fed in by our DIO7. So as you can see on the screen, you can see that our DIO7 here is the clock source, and DIO10, DIO11, DIO12 are our counter outputs. So you observe the count sequence on these three DIO pins, these three DIO outputs or signals or states. So my LSB is connected to my DIO10, which is the QA, which is pin 14 on the counter. And then my pin 10 on the counter from the counter output is connected to DIO12. And so as I toggle my counter by toggling DIO7, I use that to toggle the clock, which serves as the input of the counter. You can see that for every toggling, the count sequence increments by 1 from 0 to 7, and it rolls back to 0. So that is how we implement our count sequence to verify the correct operation of our counter. And that's all we need to do for step 1. So for step 2, we'll be needing our counter setup from step 1 into step 2. So in step 2, we're trying to verify the correct operation of a multiplexer. If you remember very well, that a multiplexer basically propagates a particular input to the output based on the select signal. So the select input for an 8-input multiplexer will be 3 bits. So meaning that between 0 and 7, we can use those 3 bits to select an input state to be able to propagate to the output. So for example, if I want to select input 2, then my select input will be a 0, 1, 0. And then whatever the state of input 2 will be propagated to the output. So if my input is 0, then my output will be low. If my input is 1, then my output will also be 1. So to demonstrate the working operation of a multiplexer, I'll be showing the connection here. So to implement my select, I'm using my counter output that we use in step 1. So I have here the second counter wired up as the first counter. The same DIO that feeds the first counter feeds the second counter through this purple wire and goes through this green wire into clock input 2. I still have my ground and my 5-volt connections with the white wire and the red wires respectively. Then I have the output of my counter, which is indicated by my QC to my QA, my QC, which is pin 10, and my QA, which is pin 12, all connected. And through this green wire, I'm feeding my multiplexer select inputs. Then my DIO 0, which is indicated by these purple wires, to my DIO 6, I feed this feeding the inputs of the multiplexer through this purple wire and these yellow wires. So I have my DIO 0 to DIO 3 here, and I have my DIO 4 to DIO 6 on the right side of the multiplexer. And you can see the wiring of the multiplexer in table 3 of the lab manual. So how does this work? When I toggle the input of the clock source and the count sequence starts or increments, that basically also changes the select input state. And so depending on the select input state will determine which of the inputs gets propagated to the output. I'm using my DIO 0 to DIO 6 to determine the state of the input. And the state of the input will propagate to the output depending on the select signal or the select input. To demonstrate that, I'll be showing us the result of this operation on the digital reader So, like I said, my input are being supplied by DL0 to DL6, which is DL0 to DL6 on the writer. My clock source is DL7. And then my output of the multiplex output is my DL15. So give attention to DL15 and give attention to DL6 to DL0 to DL6, and look at the clock state as well, the clock input as it toggles. So also to mirror that, I have my counter output to see exactly what the select state is by these red wires connected to the onboard LEDs. So LED 0 is my LSB and LED 2 is my MSB. So to implement that, I'll be toggling the clock and you see how the select state changes based on the count states. So at this state we have it's 0. So what does that mean? It means that if I change the state of 0, which is the DL0, which is basically the first input of my multiplexer, which is DL0, which is the DL4. So which is pin 4 here. So pin 4 here is input 0. So when I toggle, because input 0 is 0, right? So it means 0 propagates from here to the output. If I toggle 0 here, you can see that to 1, state 1, you can see that 1 propagates from the inputs, which because the select input is selecting input 0 on the multiplexer. So, and input 0 is high, is on the active high. So it means that the output will be high as indicated by my DIO 15. So if I increment the clock by toggling the clock, you could see that the select state or the counter as incremented by 1. So its count state is 1. Now, if I toggle pin 0, which is this, it doesn't affect the output because now what is being selected, the input selected is input 1, which is pin 3. So when I toggle DIO1, you can see that the state of DIO1, which is pin 1, which is pin 3 of the multiplexer, gets propagated to the output. And the same for DIO2, which is the count state is now 2. If I do that for DIO3, because the count state is now 3, I have that propagated. DIO4, because count state is now 4, select the count state, which is basically determining the select input, select that. If I toggle any other input, they do not get propagated because they are not selected. So that's basically how to demonstrate the correct operation of a multiplexer. So next we'll be going is to implement a decoder or a demultiplexer. So to verify the correct operation of your decoder, wiring connection of the first two stages, that is your counter and your multiplexer, you need them to together with your decoder to implement your step 3. So table 4 shows us how to actually connect our decoder and also connecting the wires from the multiplexer and the counter into our decoder. So what we're trying to set up here is to set up a multiplexer, demultiplexer circuit. And what does that imply? It implies that when the selects a particular input on the multiplexer, the state of that input gets propagated to the output of the multiplexer, and that same select combination that selects the input that gets propagated to the output also selects the output of the decoder. So, for example, if the select input is a 0, 1, 0, what does that imply? It means that pin 2 or input 2 on the multiplexer is selected. And so whatever the state of input 2 is, gets propagated to the output of your multiplexer. And that same multiplexer is serving as an input into our decoder or the multiplexer. So the same select, which is 0, 1, 0, also selects output 2 on the decoder. So meaning that the state of input 2 on the multiplexer gets propagated through the multiplexer output into the demultiplexer input, and then that state actually reflects on the output of the multiplexer, output 2 of the demultiplexer. So if any other output is being checked on the demultiplexer, you could see that you won't be able to actually access them because the select signal basically selects which of the outputs is being checked or is being checked at a particular time. So that's actually how a modulation and a demodulation principle works or in real application. So to implement that, I'll be showing us how this is wired up. So what I have here is I already have my counter state is at state 0, meaning that it selects bit is at 0, 0, 0. And so 0, 0, 0 feeds the multiplexer to select input 0. And so the state of input 0 gets propagated to my multiplexer output. And then my multiplexer output is being fed into my decoder input. And so through this purple wire, as you can see here, and then I have my counter states feeding through these yellow wires, feeds the select input of my decoder. And then my output through this white wire and this purple wire feeds the LED. So if you look closely at the LED, you will see that LED 0 is off. Why? Because the select is selecting the output 0, selecting input 0. So the state of input 0, which is indicated by my DIO 0, is 0. So when I toggle this to 1, you will see that 1 gets propagated to my output Y, which is indicated by my DIO 15. And then that 15 gets propagated because now output pin 0 is selected by the select signal from the counter. You will see that LED 0, which was formerly off, is now on because the input here is the state has changed from 0 to 1. So likewise, if I toggle back to 0, you see that the LED 0 has gone off because the port selected is at state 0. If I increment my counter to 1 by toggling the clock, is at 1. If I toggle, you will notice that LED 1 is off. If I toggle my DIO 1, which is the second input into my multiplexer, that gets propagated to the output as indicated by DIO 15. And you could see that also DIO 15 gets propagated, or the multiplex output gets propagated to my LED 1, which is the second input here. So the state gets propagated to this. If I toggle DIO 0, it doesn't affect, the first input does not affect it because it's not selected. If I toggle any other inputs, they do not get selected, but the particular input that was selected gets toggled, and that you can see. And so if I run it through, so let's assume that I leave all the input at state 0, you would see how these zeros get propagated through the multiplexer to the output of the multiplexer. So the selected input gets propagated to the selected output of the corresponding selected output. So if you observe the writer and the reader on the screen, you see that as the counter counts up from 0 to 7 back to 0, you will see that the LED also, they begin to go off at the particular selected inputs, because that states all the input states are all 0. So that's what you are expected or is expected of you for step 3. And that's all for lab 3. Hope this is helpful. If you have any question, you can reach out to your GTA. All right, have a good day. Thank you.